Hello and welcome back. In the previous video, I introduced Coulomb's law, which gives us a way to calculate the force that is exerted between charged particles. And in this video, I'm going to talk about another way that we can calculate the force that is exerted on a charged particle. And this is by using something called the electric field. And to understand what an electric field is, I first want to just briefly talk about the history of electric fields so that you can understand kind of where this idea came from. So, 200 years ago, when Isaac Newton was coming up with this universal gravitational theory, and Coulomb was coming up with this force that is exerted between charged particles, around this time, people were starting to wonder how it is that two objects could exert a force on each other, even if those objects aren't in contact with each other. So in other words, how is it that the sun can exert a force on the Earth if the Earth is not in contact with the sun? And around this time, there were two different schools of thought. Some people said that, there's no problem with two objects exerting a force on each other, even when they're not in contact with each other. And this was called action at a distance. Other people said that two objects could not possibly exert a force on each other unless they're actually connected some way. And this thing that was connecting these objects, they called a field. And so this is the whole field theory approach to understanding how objects can exert forces on each other even when those objects are not in contact with each other. Now at this point you might be wondering whether or not we need fields to describe electricity and magnetism. And it turns out that you really do need fields. And the reason is that an electric field not only exerts a force on charged particles, but changing electric fields can actually create magnetic fields. So you can't come up with a complete description of electricity and magnetism without introducing this idea of the electric field. Of course, people didn't know this 200 years ago when they first came up with the electric field, but later on, as they began to develop this theory, they realized that it's really necessary to have an electric field in order to get a complete description of what's going on. So, what is an electric field? Well, the electric field is basically a way that we can describe the tendency for a charged particle to exert a force on another charged particle. So what do I mean by this? Well, let me go ahead and open up a blank screen here. So we say that the electric field is a property of the environment. Now, what do I mean by that? Well, let's suppose I had three charged particles. Say we'll call this plus Q, minus Q, and plus 3Q. So the electric field is a property of these charges. This is my environment. And what this electric field does is it describes the force that would be exerted on a particle if I were to add it to the system. Okay, so the idea is that if I were to add a charge, we'll call this lowercase q, to the system, the electric field is going to describe the force that's going to be exerted on this charged particle when I add it to the system. And we know that the force that is exerted on this particle is going to depend on the charge of the particle that I've added to the system. Okay, so if I add a larger charge, the force will be larger. A smaller charge, the force would be smaller. Now, again, I want a property that doesn't depend on the charge of the particle that I've added. I want this to only depend on the environment. So I want it to depend on this charge, and this charge, these charges that are on the outside. I don't want it to depend on the charge of the particle that I've added to the system. Okay? So what we do is we define the electric field as being equal to the Coulomb force that would be exerted on the charged particle divided by its charge. So now this is a property which doesn't actually depend on the charge of the particle that I've added to the system. It only depends on these three charges on the outside here. So it only depends on the environment. So the electric field, again, the idea is that it describes the tendency for these three particles on the outside to exert a force on another charge if I were to add it to the system. Now, one important thing to understand about this charge that I've added here, this is called a test charge, and the idea is that I could add a test charge anywhere. So I could put it here, I could put it here, I could put it anywhere I wanted to, okay? And because of this, there is an electric field at every single point in space. So there's an electric field right here, and this electric field would describe the force that would be exerted on this charge if I were to add it to this point right here. But I could just as easily add a charge right here, and the electric field at this point would describe the force that would be exerted on a charge if I were to add it here. And the same thing with this point down here. So for every point in space, there is an electric field, and that electric field describes the force that would be exerted on a charged particle if you were to add it to that point in space. Now, one last thing that I should mention about these test charge particles. Okay, these particles don't actually have to be added to the system. This is just a way to calculate the electric field. Okay, this is sort of a conceptual thing. So this isn't like we're actually adding an additional charge to the system. It's just that the electric field is equal to the force that would be exerted on a charge if we were to add it, divided by that charge, the particle. And this charged particle that we add, we always ignore the effects that it would have on the system. Now, what do I mean by that? What type of effects could a charge have on the system? Well, we'll see in the next video that when you put charges near a conducting surface, something like a metal surface, that charged particle will actually induce a charge on the surface of the metal. And we always ignore that effect when we're calculating the electric field. So it's only a property of, the charges that existed before. Now, because the electric field describes the force that is exerted on a charged particle, and because the total force that is exerted on a particle is equal to the sum of the forces that are exerted on the particle, the total electric field that is created by multiple charges is just equal to the sum of the electric fields that is created by each of the individual charges. Now, when I first defined the electric field, I said that the electric field is equal to the force that would be exerted on a charged particle divided by the charge of this particle. Now, because we know how to calculate the Coulomb force that is exerted between 2 point particles, we can actually write down a formula for the electric field that is created by a point particle. So the idea is that if I have some point charge, let me call this Q1, and I want to know the electric field that is created by this charge, well, it's going to be equal to the force that would be exerted on a test charge, we call this Q2, divided by the charge of this test charge. So the electric field is equal to the force that would be exerted on charge 2 divided by charge 2. And we know that the Coulomb force is equal to K Q1 Q2 divided by the distance between the charges. And then we're going to divide all of this by Q2. So we see that Q2 cancels, and the electric field that's created by Q1 is just K Q1 divided by R squared. So it's a very simple formula for a single point charge. Now, this gives us the magnitude of the electric field that's created by a point charge. Now, how do we find the direction of the electric field? Now, because the electric field is defined as being equal to the Coulomb force divided by the test charge, we can see that the electric field will always point in the same direction as the Coulomb force as long as our test charge is a positive charge. And the reason that the sign of the test charge is important is that remember that if you multiply or divide a vector by a negative scalar, you actually flip the direction of the vector. So as long as I make my test charge a positive charge, then these two things will point in the same direction. So what if I have a positive point charge? Well, if I place a positive test charge outside of this positive point charge, remember, like charges repel, so this positive test charge will be pushed away from this positive charge. And that's true no matter where I put my test charge. So if I put my test charge right here, it'll feel the force pushing away like this. If I put my test charge here, it's always going to point away from this center charge. So what this means is that the electric field that's created by this charged particle, it always points away from that charged particle. Conversely, if I have a negatively charged particle, well, if I put a positive test charge outside of a negative particle, remember, opposites attract. So this positive test charge is going to be drawn towards this negative particle. And again, that's true no matter where I put my positive test charge. It's always going to be pulled towards this negatively charged particle. So the electric field that is created by a negative charge always points inwards towards the negative charge. Now let's go ahead and look at a couple of examples. This first example says, all the charges in the figure below are plus or minus 2.4 microcoulombs. And again, remember, red is a positive charge and the yellows correspond to a negative charge. The question asks us to calculate the magnitude and direction of the electric field at the center of the charge distribution. So at this point right here. Now it turns out there's actually a little bit of a trick that we can use to simplify this problem. So I say here, what can we say about charges Q1 and Q4, or the electric field that's created by Q1 and Q4? Well, if we think about adding a test charge to the center of this distribution, now remember we always consider a positive test charge. Well, this positive test charge is going to be repelled from Q1. So Q1 would exert a force looking like that on this test charge, and Q4 would exert a force that looks like this on the test charge. Now looking at these two forces, we can see that they point in opposite directions. And because they're both the same distance from the test charge and they have the same charge, these two forces will perfectly cancel. So we can actually ignore these two charges over here when we're calculating the electric field at the center of this distribution. Now what about the other two charges, Q2 and Q3? Well, if I put a positive test charge here, it will be attracted to the negative charge here. So the force that's created by Q2 points like this, towards Q2. And the force that's created by Q3 is going to point away from Q3, because like charges repel each other. So Q3 points like this. So what we can see is that the electric field that's created by Q2 and Q3 are going to be the same. They're going to point in the same direction and they'll have the same magnitude. They'll have the same magnitude because these are the same magnitude charges and they're the same distance from the center of the distribution. So the total electric field that's going to be created is just going to be equal to twice the force that would be exerted, let's say, by charge 2 divided by this test charge that I'm going to add here in the center of the system. So let me call this Q. And this is going to be equal to, so we have, this is 2, the force is going to be K times Q2 times Q divided by the distance squared, and then we divide by Q. So the Q's cancel, and this is just going to be 2K Q2 divided by R squared. And remember, the Q was 2.4 microcoulombs. This distance, now we got to be a little bit careful here, okay? This is 1 centimeter, and this is 1 centimeter. So the distance between this charged particle and this particle over here is going to be equal to, it's going to be 1 centimeter squared plus 1 centimeter squared square rooted. This is the distance between those charged particles. So this is my R. So this R is going to be equal to the square root of 2 centimeters. And if I plug that into this formula here, and I plug the charge 2.4 microcoulombs, I'll see that the electric field at the center of this distribution is going to be equal to 2.16 times 10 raised to the 7th. And the units of the electric field are going to be, if we think about this, this is describing the force per charge. So it's going to be newtons per coulomb. And that's the electric field at the center of this charge distribution. Now let's go ahead and look at another example. So this example tells us that the electric field at the center of the circle shown below points vertically upwards, and we're asked to find the ratio of these two charges. Now remember that the electric field points in the same direction as the force that would be exerted on a positive test charge. So because the electric field at the center of the circle points vertically upwards, we know that the total force that would be exerted on a positive test charge has to point vertically upwards. And what this tells us is it tells us that these two charges at the bottom have to both be positive, because the positive test charge at the center of the particle is being repelled, it's being pushed away from these two charges at the bottom. Now, because we know that the total electric field points vertically upwards, what this tells us is it tells us that the x component of the two electric fields that are created by Q1 and Q2 both have to cancel. So for example, Q1 creates an electric field that points like this, and it has some x component, I'll call that QX1, and Q2 has some electric field that points like this, and it has an x component that I'll call QX2. So this is the electric field that's created by charge 2. And these two x components have to cancel. So the x component of the electric field that's created by charge 1 is just equal to the electric field that's created by charge 1 times, hopefully you can see that if this angle here is 30 degrees, then this angle is also 30 degrees. So the x component of the electric field that's created by charge 1, that is opposite this angle. So it's going to equal the magnitude of the electric field that's created by charge 1 times sine of 30 degrees. It'll be sine because this x component is opposite the angle 30 degrees. And we know how to calculate the electric field that's created by a point charge. This is just kq1 divided by r squared times sine of 30 degrees. Similarly, Ex2, the x component of the electric field created by charge 2, is going to be kq2 over r squared times sine of 60 degrees. Now, because these two x components have to cancel out, we can set these two x components equal to each other. So if I do that, I have kq1 over r squared times sine of 30 degrees has to equal kq2 over r squared times sine of 60 degrees. And if we do that, we can see that the k's will cancel, the r squareds will cancel, and then if I solve for q1 over q2, I can see that that is going to be equal to sine of 60 degrees divided by sine of 30 degrees. And if I plug that into a calculator, I see that this is equal to 0.577. So this is a little bit more of a challenging problem because it really dealt with the vector nature of the electric field. So let's go ahead and look at one more example. This last example says, an electron is initially moving in the x direction with a speed of 7 times 10 to the 6 meters per second. The electron enters a region with a uniform electric field which points in the y direction. The electron is displaced 1.5 times 10 to the minus 2 meters in the positive y direction after traveling 2 times 10 to the minus 2 meters in the x direction. The question asks us to determine the magnitude and direction of the electric field. So let me go ahead and open up a blank screen here. So as usual, I've written down the information that was given to us. So we were told that the electron was moving at a speed of 7 times 10 to the 6 meters per second in the x direction, and that the electron is displaced by 1.5 centimeters in the y direction after traveling 2 centimeters in the x direction. And because this particle is an electron, we know that it has a charge of minus 1.6 times 10 to the minus 19 coulombs and a mass of 9.11 times 10 to the minus 31 kilograms. And we're asked to find the magnitude and direction of the electric field that caused this electron to get displaced in the y direction. So the idea in this problem is that there is an electric field that's pointing in the up and down direction, and that exerts a force on this electron, causing it to get displaced in the y direction. Now we can find the relationship between the electric field and the force by using the definition of the electric field. So the electric field is equal to the force that would be exerted on a test charge divided by the charge. So if we solve for the force, we see that the force is equal to the test charge times the electric field. And it turns out that we can actually use this formula to calculate the force that is exerted on any charged particle when we're given the electric field. So because the electron has a negative charge, the force will point in the opposite direction as the electric field. So in this case, we're told that the particle gets displaced in the positive y direction. So there is a force that is pushing on this electron that points in the positive y direction. This tells us that the electric field has to point in the negative y direction. So we have an electric field that points downwards like this. And that's going to exert a force on the electron that's going to point upwards. And that's going to cause the electron to travel in this path that I have shown here. So how do we actually calculate the electric field that's being exerted on the electron? Well, if we think about this, there are no forces that are being exerted in the x direction. So this means that the electron will move at a constant speed in the x direction. Now we're told that the initial speed of the electron was 7 times 10 to the 6 meters per second, and that the electron travels 2 centimeters in the x direction. So using this, we can figure out the amount of time over which this force is being exerted on the electron that causes the electron to move 1.5 centimeters in the y direction. So we know that the velocity in the x direction is equal to delta x over delta t. So solving for delta t, we see that delta t is going to be equal to delta x divided by Vx. So now what we need to do is we need to relate the force that's being exerted on the electron to its acceleration, and then finally relate that acceleration to this displacement. So we know that the force that's being exerted on the electron is equal to the charge of the electron times the electric field. And we know that this is going to be equal to the mass of the electron times the acceleration of the electron. So solving for the acceleration, we see that it's going to be equal to QE divided by the mass of the electron. And this is the acceleration in the positive y direction. Now because the electron is initially traveling in the x direction, it initially has no velocity in the y direction. So the displacement in the y direction will be given by 1/2 ay delta t squared. We don't have to worry about the other term because it'll be 0 because the electron was only moving in the x direction initially. So I have a formula for delta t, I have a formula for the acceleration, and so I can actually plug all this in. So I see that delta y will be equal to 1/2 times the acceleration, which is eq divided by the mass of the electron, times delta t, which is delta x divided by Vx squared. And now if I solve for the electric field, I'll see that the electric field is going to be equal to 2 times the mass of an electron times delta y divided by E, that's the charge of the electron, and I'm going to multiply all of this by, it's going to be delta x, Vx divided by delta x squared. And now if I plug all this into a calculator, I see that this is going to be equal to 2.09 newtons per coulomb. So this is the magnitude of the electric field that causes the electron to be displaced by 1.5 centimeters. And now the last thing I want to talk about in this video is something called electric field lines. And basically what electric field lines do is they allow us to easily visualize the strength and the direction of the electric field. And we've already drawn some basic electric field lines. For example, we said that when we have a positive charge, the electric field always points away from the positive charge. And this picture down here basically illustrates the electric field lines for a positive charge. So we can see the electric field is always pointing away from the positive charge. Likewise, we talked about the electric field lines for a negative charge, and we said that these lines are always pointing inwards towards the negative charge. Now I want to talk about some basic rules that we can use to draw the electric field lines for more complicated charge distributions than just a single charge. So the rules that we have for drawing electric field lines is that the electric field lines always point towards the negative charges and away from the positive charges. Now something that you might find useful, sort of like a trick to help remember which direction the arrows are supposed to point, I always like to think of the positive charges as being like a high point. So later on we'll talk about how you can think of the voltages as being like a topographical map. But what you can do is you can think of the positive as being like a high point, like on top of a hill or a mountain, and the negative as being like a low point, like in a depression or something like that. And these arrows would point in sort of the direction that, like rain would flow. So if it's raining, it's going to flow from up here to down there. So the arrows point from the positives to the negatives. The second rule that we have for drawing electric field lines is that the electric field lines will always begin and end at either a charge or all the way out at infinity. So for example, here we have these electric field lines are starting on the positive charge and then they're extending out to infinity. Here we have these electric field lines are starting out at infinity and they're pointing inwards towards a negative charge. The third rule that we have for electric field lines is that the electric field lines never cross. And then finally, this last thing is basically a way that we can interpret the strength of the electric field. And this says that the more closely spaced the electric field lines are, the stronger the electric field. So for example, if we look at these two charges here, when we're really close to the positive charge, we can see that these lines are more closely spaced. When we go further away, the lines become more spread out. So this corresponds to the idea that when we're close to a charge, the electric field is stronger, and when we're further away from the charge, the electric field is weaker. Now let's go ahead and look at a couple of examples. So here I've placed a positive charge next to a negative charge, and now I want to draw the electric field lines that correspond to the total electric field caused by these two charges together. Now there's a couple of tricks that we can use to help us draw the electric field lines. One trick is that when you're very, very close to a charge, the electric field lines look more or less like they would if the charge was all by itself. So for example, I know that when I have a positive charge, I just get these arrows that are pointing away from the positive charge, and they're just going to kind of go off in straight lines like this. Similarly, if I have a negative charge, I'm just going to have these straight lines that are coming inwards towards this negative charge. So let me just go ahead and draw those. And as long as I'm really close to the positive charge, or I'm really close to the negative charge, these lines are always going to look the same. Now we said that the lines always point from the positive charge to the negative charge, so now I just start connecting them. Now here, I've already started going off in this direction, and because they can't cross, this one's going to have to meet up with this line over here. So I'm forced to go up here, I'm going to be going down in this direction over here, so the line I'm going to draw looks something like this. And then, didn't draw that very well, let me try that again. Something like that. And then I just kind of do this for all of these lines. So these two are going to connect like that. These two are going to go even further away, and then they're going to come back like this, right? Because this one's going real steep, right? It's going vertically upwards, so it's going to take longer for this line to curve. So it's going vertically upwards, it gradually curves over, then it comes back. This one's actually going away now, so it's going to go away like this, and it's probably going to go all the way off screen, turn around somewhere above the screen, and then it's going to come back around up here. And again, we have to draw these arrows. Remember, they go from the positive to the negative. And now these lines right here, this one's probably just going to go all the way off to infinity. This one will go all the way off to infinity as well. And then this line's going to kind of come around like this. So this is how we draw these electric field lines. Now one other trick that I want to tell you about, so I mentioned here that if you're really, really close to a charge, the electric field lines basically look like they would if the charge was just by itself. Now it turns out that if you're really, really far away, you can basically treat the two charges as sort of like a sum. What I mean by that is, so if I have a positive charge here and a negative charge right here, if I look at the electric field line that's caused by this, so if I'm really far away, I get an electric field line like that, some like that. Then I get some lines that are further away like this. And the idea is that if I'm really, really far away from this charge distribution, for example, if I'm like way out over here, I really just don't see any electric field lines anymore, right? So if I'm like really, really far away from these two charges, then the thing is that I've got a positive charge here, I get a negative charge here. If they're equal charge, if I'm really far away, it just looks like they've canceled out. So that's why, for example, if you have a neutral atom, you have the same number of protons as electrons. When you're really far away from that atom, you really don't see any of those charges. It just looks like a neutral object. And that's what we have here. So I've got a positive charge placed right next to an identical negative charge. And when I'm really far away, these electric field lines, they become really, really far spaced out. So the electric field is really, really weak. So now what happens if I have two positive charges? Now remember, the electric field lines cannot cross. So again, if I'm really, really close, the electric field lines look like they always do. So I get these kind of straight lines that are coming away from this positive charge. Same thing over here. I get these electric field lines that are going away from this positive charge. And if we think about this, we know that if I'm right here in the center, I have an electric field from this positive charge. It's pointing away like this. And from this charge, I get an electric field line that points away like this. And at the center, those two things are going to cancel. And in fact, if I'm anywhere along this dashed line right here, which is perfectly between these two charges, the electric field in this x direction will cancel out. So my electric field lines are going to look something like this. I'm going to have an electric field that's going to kind of come up like this, and it's going to go away like that. So this gives you kind of an idea of what the electric field lines look like when you place two charges next to each other. So these lines that would normally come towards each other, because they can't cross, they kind of go towards each other and then they get diverted away, and they're going to asymptotically start to approach this dotted line. So if I have other field lines, it'll also kind of go like this. And then if I'm on the opposite sides, like for example if I'm over here, the electric field lines are pretty much just going to act almost like normal. And again, if I'm really, really far away from this, let me go ahead and just draw another picture. So if I have two charges that are really, really close together, and they're both positive charges, so I get this kind of dashed line right here, what's going to happen is that the electric field lines are more or less going to look like they always do if I just had a single positive charge. So we can see now if I'm looking at this really, really far away, if I'm way out here, it basically just looks like a single positive charge. These two positive charges, when they're really, really close together, they basically just look like a single positive charge. Now let's go ahead and look at one more example. This is a little bit more complicated. Here I've got three different charges, and I'm asked to draw the electric field line for these three charges. So the idea is that here we've got two positive charges. So they're going to repel each other, so we'll have that same kind of thing we had before. Now because this is a stronger charge than this charge, it's going to cancel kind of closer to here. So let me kind of draw a little dashed line right here. And because these are opposite charges, we'll have those electric field lines that go from the positive charge to the negative charge. So let me go ahead and try to draw this. So we'll have maybe something that looks like this, something that's going to go like this, a couple more lines that go like this. And notice that I'm drawing more electric field lines from this positive 2 charge than I have from this positive charge, because the electric field will be stronger coming from this positive 2 charge. Over here we'll have electric field lines that are going to go asymptotically away from this dotted line. Have the same thing happening here for this positive 2 charge. I have these electric field lines coming off of these positive charges, and then over here in this negative charge we'll have some electric field lines that will be coming in. And maybe these two will kind of wrap around at some point, and these ones as well. So this just kind of gives you it's a real rough sketch, and anytime I ask you to draw the electric field lines for something, I'll just be asking you to do something like this, just a real rough sketch, just to make sure that you kind of can visualize what the electric field is going to look like, so that if I say, like if I put an electron over here or a point charge, which direction is it going to move, you should be able to kind of guess what's going to happen. Okay, and at this point I think I'd like to end this video, and in the next video we're going to talk about conductors and how they react to external electric fields.